today. At first, I will give a brief introduction to our company. Some of you might be familiar with us already, but it's good to recap anyway. After that, I'll tell you some background how we ended up to use Bathymetric LiDAR as a hydrographic survey tool. And believe me, it was not an easy step either for us to start using this revolutionary new technology. After these first two sections, Mikko will eventually take the command by presenting the technical ability of our LiDAR sensor. As a cherry on the top of the cake, Mikko will also open some of our completed customer cases to show how this all works in practice. And at last, we will have the questions and answers section, and we can also have some open discussion, of course, if there's still time remaining. But we try to respect your time, and therefore we stick in the schedule, and overall duration will be the maximum 1 hour today. Yes, so next, some company history. This picture might be a bit complicated, and not least because of some Finnish words there. Don't let it bother you, as the main purpose of this chart is just to present the current fragmentation of state-owned maritime cluster in Finland. Arctia is a relatively new company, established as a limited company in 2010. Since then, Arctia has been a limited company with 100% government ownership. Our roots are coming from Finnish Maritime Administration and its predecessors. Finnish Maritime Administration discontinued in 2010, and all functions were split to several companies and governmental agencies. Generally, to put it simple, operational functions were moved into established companies, and on the other hand, administrative functions were merged in governmental agencies. Our hydrographic survey department has been a part of Meritaito Ltd since 2010, and after that, in 2018, Meritaito Ltd became a subsidiary company of Arctia Group. Nonetheless, we are still using the Meritaito brand, especially for hydrographic surveys. So next up, our business areas. First, our largest business area is icebreaking. We own and operate a total of 8 large icebreakers. These icebreakers are mainly operated in Finland and during the winter season. We also search opportunities to charter out the icebreakers during the summer season. At the moment, winter season is ongoing here in Finland, and we have 6 icebreakers operational at the moment. They are mainly assisting ships to Finnish ports in difficult ice conditions. Fairway services are maintaining waterways in Finland. We maintain most of the aids to marine navigation devices in Finland, both coastal and inland waters. Our versatile maintenance fleet is present in Finnish coast, and we are also performing various tasks from oil spill management to marine construction works. We also run an own factory, which is producing spar buoys and other aids to navigation for international market. And third business area, hydrographic survey department, is specialized in underwater survey projects. We serve hydrographic offices as well as other public agencies and private companies who are willing to map underwater environment. In addition to airborne bathymetric LiDAR, we also own and operate multiple survey vessels in many sizes. These are mainly equipped with acoustic survey instrumentation. We also perform geophysical and geotechnical survey scopes for various underwater infrastructure projects. And our fairway and port design experts can analyze survey results, and further interpretation can be carried out to support our customers for fairway and port design, for example. So, going towards the main agenda today, how we adopted BathyLiDAR technology. On the screen, you can see an image from Finnish archipelago. There are thousands of islands and variable bathymetry through the coast. It's very beautiful nature environment, especially in summertime, but it can also be a very challenging environment for hydrographic mapping or nautical charting. Maritime navigation is challenging as the shipping fairways are passing between islands and in some cases bypasses very close to the beach. And please note that there is no regular tidal change here in Baltic Sea. We have been cooperating with Finnish Hydrographic Office, nowadays named Traficom, for a long time. And it's really not an easy task for them to be responsible for nautical charting in this area. The archipelago is very scattered, and those small islands and rocks are continually breaking the water surface. Generally, waters are very shallow also between the islands. And all merchant ship fairways are accurately surveyed, but there are poorly surveyed areas too, especially in shallower depths and in remote locations. Let's move forward. In the past, we have been surveying the shallow waters by small boats equipped with acoustic survey instruments. You might know that acoustic hydrographic surveying requires dedicated procedures when operating in shallow waters. Multi-beam echo sounder is not always very efficient in shallow waters, as the survey spot is getting narrower when the bottom raises up. There is also a significant risk for equipment damages or even losses in shallow waters. An unchartered shoal can anytime come up rapidly, and collision avoidance might be impossible. We also have some own experience with unexpected contacts between the seabed and multi-beam sonar, or between shoal and a vessel hull. These situations will always lead to financial losses, as the sonar wethead needs to be replaced, or vessel hull has to be repaired or just inspected. Therefore, multi-beam is usually used to collect the bathymetry until certain shallow limit depth is achieved. For example, here in Finland, we are using 5 meters depth limit for multi-beam echo sounder. Shallower depths were traditionally surveyed by a single beam echo sounder, which is resulting only depth profiles at defined interval distances. You can see a picture illustrating the single beam echo sounding. This is leading to significant data gaps between the survey lines in single beam dataset. We could say that there is a dramatic difference between the multi-beam and single beam data resolution, and full coverage is actually not achieved with the single beam dataset. So, in history, Finnish HO has performed multiple BathyLiDAR pilots with different BathyLiDAR systems. Water column clarity is typically poor here in Finland, and this is of course a major challenge for BathyLiDAR technology, which is an optical survey method. BathyLiDAR systems has been constantly developing in terms of water column penetration, achieved point densities, and object detection capabilities. In 2015, we piloted the Leica Chiroptera system for the first time here in Finland. There was multiple pilot areas which were located in Finnish coastline, as well as in some inland water locations in Finland. The results were promising, although there was some variation between the results from different locations. In next year, in 2016, we had, together with Traficom, a first large hydrographic survey project, including LiDAR surveys. At the first stage, all shallow data was collected also with single beam echo sounder, so the results were easily comparable. Finnish HO quickly noticed the benefits of full coverage BathyLiDAR dataset from shallow areas. Achieved depth penetration performance was also a positive surprise. TopoLiDAR dataset from coastline and islands, plus aerial photos, are also collected during the same flights, and these additional datasets are all very useful information for many purposes. Then, since 2017, Bathymetric LiDAR producing full density data has completely replaced single beam echo sounding in Finland for shallow water bathymetric mapping. Deeper waters are still surveyed with multi-beam echo sounder. Our first BathyLiDAR projects were done with the rental sensor, but nowadays we have an own Leica Chiroptera 4X bathymetric LiDAR system. And next, Mikko will tell you more about our sensor and its performance.
Yeah, thank you, Patrick. So first, we will go into some technical details, such as point density, depth penetration, and object detection. And after that, we will look into a few reference projects. We'll start with an example where typical flying height and airspeed are used. First of all, there are two lasers in the system, green laser for bathymetric points and infrared laser for topographic points. In this example, the bathy laser produces 4 points per square meter down to an extinction depth where it is not possible to get a return anymore, or the quality of the return is not good enough for a reliable observation. For Chiroptera system, the point density is fairly consistent down to the extinction depth. In the depth penetration formula, variable k is the diffuse attenuation coefficient. If you are more familiar with Secchi depths, there is a relation between Secchi depth and diffuse attenuation coefficient, but this varies depending on water type. More of this in the next slide. 12 points per square meter from topo channel can be used for detailed ground models or even building modeling, which especially in built-up coastal areas can provide additional value. Images are high resolution with 5 centimeter ground sampling distance, meaning that 1 pixel represents 5 centimeter on ground. In this slide, we go through a few noteworthy things about depth penetration and why this should be carefully studied when creating, for example, contractual requirements. First of all, many factors such as water turbidity and seabed reflectance influence the result. Also, the depth penetration formula is very hard to simplify, and a requirement of minimum depth defined by a Secchi depth factor, for example 2 or 3 times Secchi depth, is not ideal. It would be good to have a comprehensive understanding of the environmental conditions in the project area on which to base the requirements. And even better would be to base the requirements on actual data, for example, from a pilot project. Additionally, close attention should be paid to system performance details, such as the used seabed reflectance, as there can be differences on how this is presented between different LiDAR systems. Before moving to object detection, we have an image comparing LiDAR and multibeam accuracy. And from this image, we can see that there is a good correlation between these down to the LiDAR extinction depth. In these next slides, we have examples of 2 separate objects illustrating object detection performance of this survey method. In both cases, we have collected multibeam data to be used as a reference. In the first example, there is an object in a sloped topography at 6.3 meter depth. Note that in these images there is only multibeam data. On the left side is a top view where the cross-section is also defined, and on the right side is the cross-section taken from the object together with the dimensions. In this case, the object width is 2.7 meters and height 1.7 meters. Here we have LiDAR data on the left side and multibeam data on the right side. Both images are taken from the exact same position using the same cross-section area. From the images, we can see that the dimensions are corresponding, especially height is close to identical. In this second example, there is an object in a fairly flat topography at 6.5 meter depth. Note that again only multibeam data in these images. And again, on the left side is the top view, and on the right side is the cross-section with the dimensions. Here, the object width is 2.2 meters and height 1.5 meters, as seen from the image. In these images, we have again LiDAR data on the left side and multibeam data on the right side. And as previously, both images are taken from the exact same position using the same cross-section area. From the images, we can see that the dimensions and even shape are corresponding very well. In conclusion, these examples illustrate that IHO Order 1A object detection specifications can be met with this survey method. And we are of course happy to showcase more of these results, for example in a tailored meeting for anyone who is interested to know more. Next up are keys to success. In case you are still using the single beam exosounding as a survey method, here are some lessons we have learned during the transition from single beam to LiDAR. In this case, both LiDAR and multibeam are used. LiDAR for shallow areas, as well as for seamless land-to-water coverage, and multibeam for deeper areas. First of all, LiDAR data should be surveyed well before planned start of multi-beam surveys. This enables planning the necessary coverage for multi-beam with a better confidence so that there will not be gaps between two different survey methods. Avoiding unnecessary field days to cover possible gaps between survey methods means, of course, cost savings. The second important fact is that LiDAR data used as background data for multi-beam surveys is one of the most important reasons to collect LiDAR data. In the upper left image is an aerial image with visible ground. In the upper right image, LiDAR bathymetric data is represented with purple color, and one can see it is extending outwards from the visible ground areas. Topographic data is in brown color. But even more interesting are the smaller areas between the two islands. These are very shallow areas. And even though the laser hasn't captured anything else from the surrounding areas, these two small shallows or shoals are of great importance for the multi-beam survey, as now these are known beforehand and the multi-beam vessels can avoid these. Lastly, environmental factors such as locally changing water turbidity play a very large role in how successful the survey will be. The environmental conditions are also changing or can change very rapidly. Investing time and money to monitoring the conditions will pay up at later stages of the project. Basically, perfect timing can mean good and clean data, which is fast to process, whilst the bad timing can mean very noisy data, not fulfilling the specification, or even no data at all. In the left image, you can see satellite image with various levels of turbidity. In the right image, we have turbidity analysis derived from the satellite image. In this image, the different levels of turbidity are very clear. Blue color means good water clarity, while red and blue mean very bad turbidity. We ourselves have used second measurements taken in the field, satellite images together with analysis derived from these, and for the first time at the end of last year we tested turbidity sensors that provide real-time observations. These turbidity sensors have proved to provide crucial information when making the decision whether to fly or not at a specific time. But still, the best way to assess the situation is to use all possible methods, and this requires time and effort. In conclusion, the best possible result can be achieved with a long enough project window, enabling proper monitoring of the environmental conditions. So next we will look into some of the projects we have done in the past. We will start with our biggest client so far. Finnish Hydrographic Office, nowadays known as Traficom, ordered a pilot project in the end of 2015. The following year, they ordered a project where LiDAR was used for the first time in production. This first project was 400 square kilometers. In the next 2 years, the project sizes grew, but in all of these, both multi-beam and LiDAR were ordered at the same time, which was not ideal, as explained before. The last project started in 2019, and this is 4,000 square kilometers. That would be 10 times bigger than the first one. And in this project, the surveys were done with only LiDAR, with the intention to collect multi-beam data after finalizing this project. So it took some years, but finally we have reached the ideal order for the survey methods. Also, this growing magnitude in project size points out that the method has been indeed well adopted in the Finnish hydrographic survey projects. Next up is one of the most challenging projects or project areas we have done. The project area is the island of Sylt and its surrounding areas. This area has been surveyed several times in the past for topographic monitoring purposes. The island is located west of the border between Denmark and Germany. Customer in this project was Landesbetrieb für Küstenschutz. Here are two images taken from the aircraft, so you can get some idea of the survey area. So why was this project challenging? First of all, the bottom material consisted of fine sand, which was moving all the time, and in windy conditions causing also turbidity. Secondly, during calm days with little wind, the water quality was actually so good that near the shoreline, the laser pulses were too strong for the receiver. Basically, this meant flying to nearshore areas with lower power in the laser. And lastly, the changing bottom topography caused some headache when cleaning the data, as there could be two sea bottoms in the data, depending on how much the sand had moved. And bear in mind, this was with the whole area flown with only 2 flights. Here we can see examples of the depth and point density coverage. In the left image, we have the depth represented by 3 colors, blue color being the deepest. In this case, at least 8-meter depths were collected consistently. And in the right image, green color means over 5 points per square meter. And in this case, the whole area was covered with minimum 5 points per square meter. Despite all the challenges, in the end, the project proved to be a success and one of the most successful ones done in monitoring the topography of Sylt. The last example project is something a bit different. This was done for an electricity company called Fortum. The project area covered one of their hydroelectric power plants and its surrounding areas. They already had multi-beam data collected earlier, but this dataset didn't cover the shallow areas. So at the end of last year, we surveyed a big part of the river and of course the power plant itself with LiDAR. In the image you can see RGB colored point cloud with the bathymetric part in light to dark blue color. The reason for such bleak colors is the timing of the survey flight, which was executed in last November with winter just around the corner. Here we have a few more images. In the left one we can see the project area. In the top right, point cloud with classification shown in different colors. And in the bottom we have a cross-section of the data. The client was very happy with the results, as now they have data also from the shallow areas as well as from the river banks. This information is used among other things for water flow estimation, and erosion monitoring. And most likely, this will not be the last river B survey. So this was the end of the presentation part, and now we would be happy to answer any questions you might have.